Welcome to today's webinar. The topic today is data exchange between Rhino Grasshopper and RFEM. My name is Andreas Hörold. I will be the moderator of the webinar today. I am responsible for marketing and public relations. For instance, the Dlubal website, press releases, webinars, etc. My colleague Lukas Sühne will be the presenter today. He's responsible for the interfaces in RFEM and RStab, customer support, and so on. On the right side of your screen you can open a control panel where you can ask questions via chat. I will try to answer them. If you don't get an answer during the webinar, because there are too many, you will get an email after the webinar. The other maybe better way is to watch the entire webinar and then email your questions to info@dlubal.com. To the content of today's webinar, Lukas will say something about the features of the RFEM interface to Rhino and Grasshopper. Then he goes directly in the programs and shows the data exchange between Rhino and RFEM and between Grasshopper and RFEM. After the live presentation, he's going to say something about the plans for the future with the interfaces. Okay, that's all from my side. I hand over the screen to Lukas. Just a moment. Lukas, it's your turn.
Thank you very much for the introduction, Andreas. Welcome also from my side. I hope you can see my screen. I will quickly switch between the PowerPoints.
Yes, we can see it.
Okay, thank you very much. Then, well, you introduced the agenda already for today. I can jump directly into the description and the explanations of the interface between Rhino and Grasshopper. Now, usually we name it in one sentence, the interface to Rhino and Grasshopper. In general, that's okay because Rhino and Grasshopper are from the same developer, the McNeil Group. If we talk about the interface itself, we have to divide, however, a little bit between them. We have an interface to Rhino and one interface to Grasshopper. I will start with the interface to Rhino. For those of you who haven't heard about it before, Rhino is a general 3D CAD software. It's specialized on NURB lines and NURB surfaces. With these NURB lines and surfaces, you can create anything from a simple 2D line up to complex freeform surfaces. With these possibilities and many user-friendly features, the area of applications is huge. Not only for architectural design, so you can't just use it for architectural design. I also found examples from the automotive sector, for furniture, tools, machines, even for kitchen devices. I found examples that have been modeled in Rhino. Additionally to these modeling features, Rhino also has strong rendering and visualization tools. Since you can use Rhino in various ways, and the fact that also a lot of our customers use it, we decided to start developing an interface for it. Today, I want to show what we accomplished so far and what we also released recently. So, regarding the release itself, we released the interface with RFEM version 5.21.02 in December. If you want to install the interface, you have to install Rhino first on your PC. You require version 6.20 or newer. Then you can install RFEM and the interface will be automatically installed. If you have issues with the installation, feel free to contact our support. Regarding the export itself, we have an export from Rhino to RFEM. The export runs via our COM interface. That means you need both applications on the same PC and they both have to run on the same time, at the same time. You can export lines and surfaces. Surfaces will be exported with the stiffness type null. We set up, or we created the export in a way that you override the existing RFEM data when you export from Rhino to RFEM. So you should be aware of that. We also have an import from RFEM to Rhino. We can import lines and surfaces again, so the pure geometry, no thicknesses, materials, or anything like that. The only difference here is that we don't override the Rhino structure when we import from RFEM. We add the RFEM structure to the existing structure. Okay, this is basically the rough overview I can give you here. I will jump directly into a small example. The example that I will show is this small greenhouse here. It's not modeled by myself. I took it from grabcat.com. So to show you the interface, I will open Rhino on the left side of my screen and RFEM on the right side. What do we have here? Again, I have this small greenhouse. It consists of glass panels that have that are surrounded by timber profiles. Right now we have the rendering mode active in Rhino, so we can see, for example, the shadows of the beams. We can of course change the display into the wireframe model to see the lines that are behind all these things. So here you can see the lines of the sections. This is what we can export to RFEM, lines and surfaces. So I can run the export by pressing the export or import icon. So I can run the exchange using one of those icons. They will show up when you install the interface. I press the export, and shortly after I get the same structure in RFEM. I got my surfaces, as I mentioned, with the stiffness type null, and additionally, of course, also the lines, for example, from these sections. So this is basically the same content. If you don't want to export the complete structure, you can use two different options. You can either select the parts that you want to export. So I selected just half of my structure. I press again the export. You can see we override the existing data. And you can also see that just half of the structure has been exported. Another option is working with visibilities in Rhino. So if you hide certain parts, then they will not be exported. Okay, so now it would be up to the quality and the data you imported in general. You could use them, you could use these data to model your analytical structure in RFEM. This, however, should not be part, or is not part of the presentation today. Nevertheless, I want to show you how such a structure could look like. So I did it before. This is basically the same structure. I used the Rhino data in RFEM to model it. I used the nodes and the lines that I got from it. And I defined some glass panels in here. I defined some timber members. And of course, you can design the structure as you're used to as an RFEM user. You can calculate the deformations, or even the stresses in the glass panels, for example. But again, this is not part of the presentation today. I want to show you now just the import back from RFEM to Rhino. As I mentioned, we add the structure that we import, so therefore I will move my Rhino structure a little bit to the side, and then I simply press the import button. we can see directly the structure that has been imported. I can see the surfaces and also more or less the lines that surround the surfaces, but no members or anything like this, simply because we import the wireframe structure. And the member is not a real object in this case, it's just a line with additional information. So we import lines and surfaces. This is basically the input between, or the data exchange between Rhino and RFEM. It's a quick tool to get your Rhino data in RFEM or in the other way around. So now I go back to my PowerPoint to give you a rough introduction about Grasshopper, and then I will also show you some examples. Again, for those of you who haven't heard about Grasshopper before, it is a Rhino plugin for the algorithmic modeling. It is a visual program language. That means you don't type your commands line by line. You have components that represent certain commands, and you can connect them, and by doing so you can create your algorithm. What can you use it for? You can use it for parameter studies or optimization routines. For example, if you have a structure with where you have to analyze different bracings, then you can do it rather quickly in Grasshopper. We have an export to RFEM for Grasshopper, so no import, just the export right now. The export also runs via using the COM interface. That means, again, both applications have to run at the same time. You can export the pure geometry, basically the same as we had it in Rhino, but additionally, you can also assign cross-sections and materials to your lines. So you can create members in RFEM, and you can also assign thicknesses or a thickness and a material to a surface to get a proper surface in RFEM. Again, with each export, we will override the existing data. You should be aware of that. To show you the interface, I prepared two examples. The first one is a very simple one. Here I want to introduce Grasshopper to the viewers who haven't seen it before. And I also want to show you how you can control the Dlubal specific components, so the ones that we added with the interface. The other example should be a little bit more realistic, but I will come to that later on. So to show you Grasshopper, I will open Rhino on the left-hand side of my PC or my screen. I will create a new file in meters. And on the right-hand side, I will open Grasshopper. Yeah, like this. How is Grasshopper set up? Basically, you have a big workspace in the center. Here you can create your code, your algorithms. The code consists of the components, and you can access these components in the tabs on the top and in the drop-down boxes for each tab. Again, in Grasshopper you can create structural elements, you can create any elements in general, you can analyze them, you can run calculations and so on. We will do a very simple example here. We will just create a couple of nodes, a curve, and maybe a surface, and export that to Dlubal, to RFEM. How can I create such nodes? Well, I could use one of the components here to create a point, how they call it. We can call up the component construct point. I just use drag and drop here. And most of the components are set up in the same way. On the left side, they have their input, and on the right side, they have their output. The input of a node is the X, Y, and Z coordinate. The output is basically the point. So what I will do now is I will copy this point 2 times. And then I can modify them. I could, for example, modify the x-coordinate of the second node by simply right-clicking on the x-coordinate and defining a value. For example, the value 3. You can see the second node in Rhino will be displayed now at a certain distance to the center of origin. Rhino in that case is now basically the viewer for what you do in Grasshopper. There are other ways how you can change the coordinates. So I could, for example, use something that is called number slider. If I enter here the number 10 and press OK, I get a number slider from, in the range of 0 to 10, and I can change the number very easily. I will connect this number slider with my x-coordinate. So now I can easily change the x-coordinate of one of the nodes. I will create another number slider, Ctrl-C, Ctrl-V, and connect it to the z-coordinate. Now I have a third point. The distance of the third point to the second point should be the same as the distance from the second point to the first point. So basically the x-coordinate is twice the x-coordinate of the second node. I can do it, of course, by a number slider where I use the value 6, but whenever I change the x-coordinate here, I would have to change it here. Therefore, I will use a different method. I can run a multiplication. You just type here multiplication, and at some point the related component will show up. And the multiplication is quite easy. A multiplied by B will be the result. So I multiply the coordinate from my second node with the factor 2, which will result, in a value twice as big, and I can connect the result with my x-coordinate of the third point. So whenever I change the x-coordinate of my second point, you can see on the left-hand side, the third coordinate will also be modified. So what can I do with these 3 points? I can create lines in between. Therefore, I could call up a line command. The input is the start and the end point. Well, I got 2 points here, so I can connect them. I think it's quite clear what's happening. I get a line between the first and the second point. I could do the same between the second and third point, but that's not what I plan to do here. My plan is to get a curve between 3 nodes. Therefore, I can call up a component that is called interpolate, and it creates a curve or interpolated curve through a set of points. So all I have to do, I have to connect these 3 points with my new component, and I get a curve. It's a very basic element. Now, not every component has just one output. Some components have multiple outputs and inputs. Here, for example, I also get the length of that curve, which I could use in any other way. I'm interested in the geometry of that output in the curve itself, because I want to create a surface based on that curve. The surface I want to create using the command extrude. So I want to extrude the shape of my curve in Y direction. I already named the command extrude. The base of my extrusion is the curve itself, so the geometry. And the direction should be the Y direction. So I double click Y, and this is my direction. Now I can apply also a factor in front of that extrusion, or of that Y component, maybe again a slider, to control the length of the extrusion. So what do I have? I have 2 simple geometric components. I have a line or a curve and a surface, and that's something I can export to RFEM. This is what I want to show you now, how you can do it. Therefore, I will put Grasshopper on the left side of my screen, and I will open again RFEM. I'm not interested in that file. I will close it. I can use this one. Okay. How can you export something from Grasshopper to RFEM? Well, when the interface, or when you install RFEM, you will get the interface in Grasshopper. So you get this new Dlubal tab here. And this Dlubal tab contains right now 3 components. The first one is basically the main component. It's called RFEM5 component. It has an input, but no real output. The output of that component is basically the export into RFEM. So anything you plug into that input will be exported to RFEM. We can do it right now. Let's plug the curve into the input, and we can see directly that the curve has been generated or imported into RFEM. I can do the same with the extrusion. The result of the extrusion is a surface. So again, I can plug it into my input here, and I get the surface in RFEM. This is already quite nice, but I mentioned we can also create members and, well, surfaces without the stiffness type null in RFEM. How can we do it? Well, this is what we do with the 2 remaining components that we have here, a member component and the surface component. The member component has 4 inputs: the geometry, which is basically the line or the curve of that member, the material, the section, and the rotation. Let's define each of them. For the geometry, I require a line or a curve. The material I can define via a panel. That's basically a plain text. I recommend to use the full name of the material library from RFEM, so you get the right material at the end. For example, steel S235 according to that code. Then you can connect your panel with the material input, and it's defined. The section also is defined via a panel right now, so I create another one. Here I can enter the name of the cross-section, for example in IP300, and connect it to the section input. Now the color of the component switched from orange to gray. Gray usually means that the component is defined and it's running. It's ready to work. There is the rotation missing. Since we define the rotation by default as 0 degree, the component is basically okay to go. Of course, we can change the rotation of a member. We can do it again maybe using a panel. Let's say we enter values from 0 to 90 degree. So here I can switch between the values 0 and 90. I could theoretically connect now this slider with the rotation. There's just a small issue. We expect the rotation in radians. This is degree for me. For me, this is now degree. So I have to transform this value into radians. It's, however, quite easy. There is a component in Grasshopper that will do it. It's called radians. So you plug in a value in degree, and it will automatically calculate radians. This is the result. This result I will plug in into my rotation, and it's good to go, basically. So we define the member, and let's just export this member now to RFEM. Let's see how it works. I plug the member into my input, and I can see directly I not just have a simple curve now, I have a complete member based on that curve. And we have here the IP300, we have our steel material, and I also have the rotation in degree, 11 degree. Okay, this is the member component. Let's define also the surface component here. For the geometry, we don't. We need a surface, so not like 4 lines or something like this to close the surface. We want to assign the additional information to the surface itself, and the surface is again the extrusion from that component, or the result from that component. For the material, I could define a new one. I can also use the existing one that I defined here. So I just drag or create another line, connection line between these two components. For the thickness, I will use again a slider. I will define the slider from 0 to 1. I do it that way because we expect here meters. So if you define a thickness for the surface, the input should be in meters, therefore the slider from 0 to 1. Okay, the last input is the stiffness type of my surface. When we exported the extrusion, we always received the null type surface, so without any stiffness. We can create here, if we want to define the stiffness type in that component, we have to use a component that is called value list. If we connect the value list with the stiffness type, we can read the types that we defined in or that we have in RFEM, for example, standard or a rigid surface or the null type. I will use a standard stiffness type surface. I can now also export the surface into RFEM. I can do both. I can export members and surfaces, so I create a connection line between both components to the input here. So as we can see, I have now a surface with the thickness of 220 millimeter, my steel material, and a standard stiffness. Additionally, I have still the beam here that I exported before, or that has been exported again. So we were able to create the basic elements in RFEM, and since everything here is still connected to the number sliders, to the parameters of the coordinates, I can quickly or update my structure just by changing the coordinates here. So the export is quite quick, that we can see directly the changes that have been made here. Okay, so this is in general a way how you can create structures in Grasshopper. Very basic example, I know. The goal was more or less to show you how you can control the input of the Dlubal specific parameters. Just a couple of additional information maybe. If you use the export component here, please flatten the input. It relates to the fact that we always expect simple lists in case you know Grasshopper much better. So in some cases you have tree-like information structures, then you have to flatten them before you export them. I can also recommend to disable the export by default and just run the export when you actually want it. Otherwise, you may override your existing structure that you have in RFEM. Okay, this is the small example. I mentioned already the other example that should be a little bit more realistic. It, however, still covers only a small part of Grasshopper and its capabilities. What have I planned with the second structure? My goal was basically following. The task here was to create a roof for a bus depot. The shape of the roof is basically a curve if you cut through the roof. And the shape can vary. So it could be longer, the width could change, the height could be different of the roof. Then the area of the roof will be cut into, or should be cut into, these triangle elements, so that later on we can place plain glass panels into them, for example. So this is the goal. a basically parametric bus station or bus depot roof that should be created in Grasshopper. To show you that, I will first of all put the Grasshopper again on the right-hand side and close this project here. I will open a specific file in Rhino. That file contains only one curve. That's the curve that defines the length of that bus or of the roof, and also the shape. You can see the curve defines the shape of the roof. Now from that curve I want to create the rest of my structure. I prepared that already. I will not do it live because I think it would take too much time. I will open it and explain what I did here. Okay, this is the Grasshopper file that I created for that job. It's basically divided in 4 groups. The first group is the input here. The input contains, first of all, the curve itself. With this component, I was able to import the curve that we saw before in Rhino into my Grasshopper file. So I can import structural elements or elements from Rhino into Grasshopper and use them. I can copy them, divide them, do whatever you want. Additionally, I defined a couple of other parameters that allow me to change the shape of my structure. For example, I have a parameter for the width of my structure. I can, oh, sorry, I guess I have to deactivate something. Just a second. Oh no, it's deactivated. So I can change the width of my structure. I can also change the height of my columns if I want so. I can also play with the divisions over the width of my structure. So if I change that parameter here, the amount of divisions will change over the width. I also have one over the length. I guess, and yeah, and then I also have 2 parameters that allow me to change the location of my columns. I just want to turn off the pipes here because they decrease the performance of Grasshopper and Rhino a little bit. So, okay, so these are my input parameters. Here I can tweak my structure. Additionally, I have 2 algorithms, one for the roof and one for the columns. I quickly want to explain the roof one. So to create the shape of that roof, I simply imported the curve from Rhino. Then I used the command that it's called divide curve. With the amount of divisions, this is basically one of the parameters of my input here. Depending on the amount of divisions, I will get later on more horizontal beams. The result of the divisions were the points on this line, and I copied these points using a linear array. Now I have a huge amount of points here, and I can create horizontal and longitudinal beams based on these points. I can do it because these points are not just simple elements. There is a data structure behind. And if I know how to use the data structure, I can easily create the horizontal lines from these points, the longitudinal lines based on these points, and also the diagonals. The result from these algorithms are these 3 different types of lines: horizontal, longitudinal, and diagonal lines. And these 3 lines I simply plugged into my member component, and then I'm ready to export the members based on those lines. The other algorithm that I have here is for the columns. Here I don't want to explain it. It had just two goals. I wanted to be able to move my columns, as I showed you before, with these two parameters. And I always wanted to create the column in the intersection point. So I don't want the column to move through the glass panel or something like this. So this was one goal, to have it always connected to one of these points. And the other goal was to have control over the height of the structure. Again, the result of these two, of this algorithm were 3 pairs of lines. And I created another member component. Here I defined a different cross-section for my columns, and I also plugged it into my export. Now I can show you what will happen when we run the export. I can activate it here, and we will get the structure in RFEM. We get the roofs, beams for the roof, and also the beams for the columns, basically. I can still use or change the structure using my parameters here. I can still change the amount of divisions over the width or over the length. Since the update is quite fast, I can see directly the changes. Another change you could do is you could change the shape of the curve, for example. So if we go back to Rhino and we change the shape of the curve, this change will also apply in RFEM. So the complete structure is very parametric, which allows us to do quick parameter studies, for example. Now with the structure in RFEM, you can of course continue. You could define your nodal supports, maybe a couple of loads. I will use only the self-weight here and run the analysis. Okay, so this should have been a little bit more realistic example. Again, the possibilities in Grasshopper are much bigger. You could analyze structures, or you could run optimization routines in here automatically using different plugins that exist. I tried to keep it simple here. I hope you were able to get a rough overview about Rhino and Grasshopper. And I can also imagine that you have already some ideas which components you would also need for that. Therefore, I will go back to the PowerPoint to discuss a little bit the upcoming features and maybe also the future. Regarding the upcoming features, we definitely plan to create, or we definitely plan to insert additional components that deal with the support in Grasshopper. And we also want to update the member component that we are able to define member hinges in Grasshopper. Another topic is that we want to consider the units during the export and import to Rhino. That is a little bit an open topic right now. And then there are a lot of ideas for the future. Some of the ideas are to control, for example, the member rotation via a help node, the loading in Grasshopper. I mean, apply loads already in Grasshopper so you don't have to define them again and again in RFEM, and maybe also the import of results from RFEM back to Grasshopper to use them in additional optimization routines. I can only ask you to send your ideas to us so we get a feeling which features are required, and I hope we will and can consider them in future. That's it basically from my end here, and I would give it back to you, Andreas.
Thank you, Lukas, for the nice presentation. I hope you enjoyed it as well. As I said at the beginning, in the case of questions, just write an email to info@dlubal.com, and we will answer them. Just an additional information, all attendees from the United States and Canada will get a PDH certificate with the automatic follow-up email. At the end, I would like to invite you to the next webinar. I take over the screen from Lucas, just a moment. Just visit our Dlubal website, dlubal.com, and you can find the webinars under News and Events. Here, Webinars. And that's the next webinar presented by our American colleague Amy Heilig. Plate and shell modeling in RFEM is the name. It's part 1 of a 2-part webinar series, and you can register here with this button. Okay, that's also all from my side. Thank you for your attention. Have a nice day and bye-bye.